So good morning and welcome to all of you. Today we are going to discuss about the work done or the energy expended in moving a point charge in an electric field intensity E. Now consider a point charge Q placed in an electric field intensity E which is acting in this direction. So once the point charge is placed there, immediately a force of QE would be acting along the direction of electric field intensity on the point charge. So because of this force, the point charge will move along the direction of electric field intensity with some velocity depending upon the force. But if I want to retain this point charge at the same place, I don't want the point charge to move along the direction of electric field intensity. If I want to make this point charge stationary, I have to apply equal and opposite force. So F applied is equal to minus Q into E. So this minus sign indicates that this force has to be applied opposite to the direction of electric field in such a way that the forces will be nullifying each other and the point charge remains stationary at the point. Okay, so F applied is equal to minus Q into E. So apart from that, if I want to move this point charge of Q coulombs through a differential length dl opposite to the direction of electric field, naturally I have to spend some energy. So the differential work done to move this point charge of Q coulombs against the direction of electric field through a distance of dl is given by work done or energy expended is equal to F applied multiplied by distance. What is F applied minus Q into E? How much distance we are trying to move through a differential length dl. So differential work done is equal to minus Q into E into dl. So in this particular example, we are trying to move this point charge exactly opposite to the direction of electric field. Electric field intensity is acting along this direction, and I'm trying to move this point charge through a differential length dl, which is in the same line as that of the electric field intensity, but opposite to the direction of electric field. But if you look at the general situation, this could be a general situation. The electric field intensity E would be acting along this direction, and I want to move this point charge of Q coulombs through a differential length dl. The difference is dl and E are not in the same line. Suppose E and dl are making an angle of theta with respect to each other. Then what is the differential work done? So what we can do is, once E is acting along this direction, what component of E acts in this direction? Because the angle is theta, E cos theta would be acting along this direction. So if I place a point charge of Q coulombs here, it experiences a force of QE cos theta in this direction. And to nullify this force, I have to apply equal and opposite force. So minus QE cos theta. That is the force I have to apply to make this point charge stationary. And apart from that, if I want to move this charge through a differential length dl, what is the work done? Differential work done is equal to F applied multiplied by dl. So minus QE cos theta into dl. So this is E into dl into cos theta. It is of the form AB cos theta. So I can write this as minus Q E dot dl. Theta is the angle between E and dl. So if this is the differential work done to move Q coulombs of point charge through a differential length dl, this is the expression. Suppose I want to move the charge through a finite length. Let us say if this is the initial point B and this is the final point A. I need to integrate this expression. So integral dw, that means W is equal to minus Q integral E dot dl B to A. So many joules. The path along which the point charge is moved from point B to point A is described by this dl. dl determines the path along which we are trying to move this point charge of Q coulombs from initial point B to final point A. So W is equal to minus Q integral E dot dl B to A. This is the work done to move Q coulombs of point charge from initial point B to final point A against the direction of electric field. Now let us see for what conditions W can become zero. First thing is E and dl are perpendicular to each other. E into dl into cos theta. E and dl are perpendicular means the angle is 90, cos 90 is equal to 0. So if you try to move this point charge of Q coulombs along a path which is always perpendicular to the direction of electric field intensity, then the work done becomes a 0. Next, if the initial and final points are same, naturally the integration becomes 0. So if you are trying to move this point charge along a closed path for which the initial and final points are same, once again work done is equal to 0. And the third one is if electric field intensity is 0. Once E is equal to 0, what is the force acting on this one? Q into E. It is also 0. So further the work done is also 0. For example, let us consider a point charge of Q1 coulombs and we are trying to move this Q1 coulombs of point charge in a circular path around an infinite length line charge of density rho L coulombs per meter. What is the work done? So for this the answer is 0 because once it is a circular path, the initial and final points are going to be same. So naturally W is equal to minus Q integral E dot dl B to A. If B and A, if the initial and final points are same, that integration becomes a 0. Suppose if you want to move the point charge from let us say point B to point A along a semicircular path, what is the value? It is once again 0 because E and dl are going to be perpendicular to each other. Due to infinite length line charge, what is the expression for the electric field intensity? Rho L by 2 pi epsilon naught or AR, or otherwise rho L by 2 pi epsilon naught rho A rho, both are same. Okay. How do you describe this DL, which is a part of this circular circle that is equal to rho d phi A phi? So the direction of DL is A phi, the direction of electric field intensity is A rho or AR. So what is AR dot A phi? It is equal to 0. Now let us look at this problem. Determine the work done to move a point charge of Q1 coulombs from point B to point A. Point B is at a radial distance of RB, A is at a radial distance of RA. And we have got the same infinite length line charge with the density rho L coulombs per meter. So what is the expression for the electric field intensity? E is equal to rho L by 2 pi epsilon naught R AR. What is DL? DR AR. So W is equal to minus Q integral E dot DL. Point B to point A means from RB to RA. So minus Q1 integral rho L by 2 pi epsilon naught RAR dRAR. So what is this value finally? Q into rho L by 2 pi epsilon naught log RB by RA. So if you look at this expression, because RB is more than RA, log RB by RA is going to be positive. On the whole, the expression for W is going to be positive. Why the value of W is positive? Because electric field intensity is acting in this direction and we are trying to move this point charge of Q1 coulombs from point B to point A against the direction of electric field. Naturally, we need to spend some energy in order to move the point charge of Q1 coulombs from point B to point A. So, energy must be spent by the external source to move this point charge because we are trying to move the point charge against the direction of electric field. Suppose if you want to move point charge from A to B, then this becomes log RA by RB. Then W turns out to be negative. So whenever W turns out to be negative, it indicates that we are trying to move the point charge in the same line as that of the electric field intensity or a component of electric field intensity. When W is positive, it means that we are trying to move the point charge against the direction of electric field or against the component of electric field intensity.